Okay, so what we're going to start with is chapter 23. We need to cover naming and chemical properties, and then we'll spend 2 days, Wednesday and Friday, on reactions, which means sometime next week, probably either Tuesday or Thursday, we'll have a test on this material. Probably end up having it on Thursday, I think. So kind of prepare yourself. Hopefully you guys spent the weekend mastering how to deal with alcohols and how to deal with ethers for the naming, because that's pretty old by now. And hopefully you guys have started in on trying to organize the practice and figuring out what you want to do. I handed out those study sheets, and so what I want you to do is think about, don't fill in everything on it. If you already know how to name them, fine, then don't bother writing down the rules for naming. But if you have trouble figuring out what reaction is occurring, start thinking about the reactions and going, how am I going to recognize this type of reaction? How am I going to know what to do with that reaction? And we'll, of course, look at some of that, if you guys ask questions or review. But, aside from that, you guys have all the tools now, right? You just have to make use of them. Did anyone do extra practice this weekend? Mostly naming or some reactions or? And how did it go?
The first couple ones I haven't done anything in a while back, but I got back and it's good.
Yeah, it's good for tune-ups, but if you notice that you had significant issues, come talk to me ASAP, because figure, start looking at the number of days you guys have left and start going, okay, I've got this many days left, so I can afford this many days on naming, and I need to spend this many days on reactions, and I have to remember that I do have other classes to work in there, right? So kind of plan out your schedule ahead of time and see what happens. Okay, so we're going to talk about aldehydes and ketones. So we've got aldehydes and we've got ketones, and they're much the same molecule in that the functional group is what we're going to learn is called a carbonyl carbon, and it's just a question of where on the molecule it is. So if I have a carbon double bonded to an oxygen at the end of the molecule, meaning notice that I've got the CH group there, versus if I've got that carbonyl carbon or that carbon double bonded to the O in the middle of the molecule. Or if we're kind of thinking about line drawings, what we're saying is that it's either going to be on the end or somewhere in the middle of that molecule. And that's the only difference between an aldehyde and a ketone, is where that functional group is located in the molecule. The other way that we should kind of consider these is we have to remember that if we're writing condensed structures, we have, for instance, CHO is an aldehyde. What if I write it like, for instance, CH3, CH2OH? What's that instead? Meaning, what's the difference between a HO and an O? If I write it that way, that's the aldehyde, right? Because that's telling me that the hydrogen is not connected to the oxygen, and it's really connected to that carbon there. Now, the computer doesn't draw it in. I like to draw it in sometimes to make it obvious that we're talking about an aldehyde. And that if I have the OH, that's talking about an alcohol. Just like for a ketone, if I have something like CH3COCH3 versus, say, CH3, OCH3. Notice that if I have a CO, that's our ketone, meaning that's just this pictured molecule. And if I have an O that's kind of sandwiched between a pair of CH3 groups, or there's hydrogens around it, that's actually showing that I have an ether like this. So when you're looking at the condensed structures, ethers and ketones look alike, and aldehydes and alcohols look alike. So you have to be very careful for them, or be very careful with them. So for naming them, the only new naming rules we have is for aldehydes, we change the end to Al. So for instance, if I had just, butane, then all I'm doing, if I throw an aldehyde functional group on that, is butan-al. Meaning I changed that E at the very end to an Al. Or we'll even write it like that. E goes to Al. And notice that there is no location. And that's because it's always at the end of the molecule. And remember, we always give our functional group the lowest possible number. And so anytime you see an aldehyde, it's kind of nice because you know automatically which end to start numbering the molecule from, even if we have, you know, say one end that's more loaded than the other end, like that. We always know that this has to be 1 because it's the aldehyde. So we got 1, 2, 3, 4, 5. Oops, that's a chlorine. So I would have 5, 5, 5 trichloro dash 4-methyl pentanal. I don't know if it's me, but I always have this desire to say that aldehydes are a little anal, retentive. I mean, I don't know. That's just my weird brain. So, aldehydes, I think, are probably one of the easiest molecules to name because you know it always gets the number 1, and all you have to do is change that ending to al. What if I have 2 of them? What do you think is going to happen? Yeah, we're going to have a pentane. Oops, that's an A and E, sorry. Pentane dial. And notice, do we need numbers for it? Not really, because there's only one spot that it can really be in for it. Okay, so for ketones, they're not much harder. Oops. Here we change the E to an ONE, and we have to remember to give the location, because it can be in more than one spot. For instance, if I have, say, a 5-carbon chain, there's 2 different spots that can be on. I can have 2 pentanone versus 3 pentanone. And of course, we always give it the lowest possible number. So if I have a choice between, say, a ketone group on the number 2 spot and, say, a Cl group over here and a bromine group over here, even though, you know, normally we want to give all the lowest possible numbers, here we're going to go 1, 2, 3, 4, 5, and so we would have 5 bromo dash 4 chloro dash 2 pentanone. So the new part of this is simply changing the endings. Aldehydes no numbers, ketones get numbers. So I have to admit, when you start looking at all the functional groups, because remember, we're going to also have to throw in alcohols that are mixed in here and ethers that are mixed in here. And so you're going to have a very clear set of rules to use for each one. But what you want to start doing is looking at the similarities and going, okay, aldehydes are always at the end, so I don't need numbers. Alcohols and ketones can be anywhere, so I better put a number on it, right? Ethers are strange in that they're really considered just a side chain, so it's like a methoxy or an ethoxy group. What if I have 2 ketones? Yep, so this is 2,4 pentane dione. And notice that we start adding that E in, like, for instance, in the pentane, so that we have better pronunciation is really, I think, why they do it. Otherwise, there's not a real good reason. It's just the way it is. We also have to remember that some of these naming rules are pretty arbitrary just because they, we have to have a rule in some cases. Now, of course, we can mix it all up. If we start getting more difficult, what are we going to do if, for instance, I have a ketone and a carbon-carbon double bond? Yep, ketones get the smallest number because they're the newest functional group, basically. And so we'd call this, let's see, 4 pentene dash 2 one. And so notice that there's my ene indicating that I've got a carbon-carbon double bond, and then we just add on as many dash numbers, dash functional groups as we want after that. Do you guys remember what we do if that functional group is an OH, though? This is 4-hydroxy dash 2 pentanone. There we go. Pentanone. So this, if it's not the main functional group, is quite often referred to as a hydroxy, if not the functional group. That's what FG stands for. Functional group, field goal. I don't know what FG stands for else, but it's what I'm using it for. So the hydroxy, if the OH isn't the main group, it's considered, I'm sorry, I should say if the OH is not the main group, we usually call it a hydroxy if it's a side chain. So we kind of name it like a side chain instead of like a functional group. If you notice, I, of course, am sick, so life is fun. So what? No, we have class tomorrow. Worst case scenario, I have Lisa teach it. It's a lab. By the way, what is it? If it's a new lab, that means it's also a lab. Okay, so what? Just the next one on aldehydes and ketones, I think. So let's take a look at that functional group again. In regards to, we're kind of thinking about what does it mean in respect to physical and chemical properties. So we said that we sometimes call this a carbonyl group. And what can you guys tell me about it? And we'll even add some more clues. So what shape does it have? That's trigonal, planar. What bond angle? And what hybridization? Just sp2. So remember, anything that has a carbon-carbon double bond, or in this case carbon-oxygen double bond, is that sp2 hybridization. And remember, that means that this bond is highly reactive. What do we know about the intermolecular forces associated with that? What type of intermolecular forces is it capable of? Yeah, just dipole-dipole. So if we look at it, oxygen is slightly negative, the carbon is slightly positive, and so that means that we can have a dipole-dipole interaction, or that it's a polar bond. Now remember, for hydrogen bonding to occur, it has to be hydrogen bonded to oxygen, nitrogen, or fluorine. Now, can a carbonyl group interact with a hydrogen bond? Certainly. But is it itself capable of forming hydrogen bonds? No. And so What do we know about the strength of dipole-dipole? Stronger than, but weaker than. Yep. So how is that going to affect things like boiling points and melting points? Where would we expect these to be in our continuum of molecules that we've talked about? What's got the lowest melting points and boiling points? Right, but what type of molecules? Things that are like anes, enes, ynes. Right, so this is the low end of the spectrum. And what's slightly above those? And we said that there's a lot of things about anes, enes, and ynes that we can talk about being linear versus globular, things like that. Alcohols are. What's less than alcohols though? So alcohols are up here. So what's the one we're missing? Yeah, ethers. And then we can throw in our aldehydes and our ketones. So we're going from something that's just pure LDF to something that has very weak dipole-dipole to a stronger dipole-dipole. And then we finally have something that's capable of forming hydrogen bonds. And so these have relatively high boiling points for the set of molecules that we've talked about so far. What about solubility? What do we expect for the solubility of these? Not the most, but the least. Notice that solubility follows melting point and boiling point for the most part. Ethers actually are fairly soluble, aldehydes and ketones, and this is relative to each other. And of course, alcohols are usually highly soluble. What do we have to factor in here, though, that's different between solubility and melting point and boiling point? No? What's the one difference sort of between them? Meaning the trends are pretty much the same. Things that have, low melting points and boiling points also tend to be the least soluble compounds too, because they only have LDF attractive forces holding everything together. What's the one thing that's different? Yeah, size. Which one has the higher melting point and boiling point? And the reason for that is? Yep. Actually, I guess I got the proportionality sign on the wrong side. And so an alcohol group certainly increases the boiling point of something, but size also matters. What about solubility? The smaller one is more soluble because this part right here is insoluble, and the OH group, or the alcohol group, is the soluble part, whereas here we have a really large part that's insoluble and just a tiny part that's soluble. So small molecules are more soluble. Large molecules have higher boiling points and melting points due to the proportionality with London dispersion forces. So what that means is even if we say that aldehydes and ketones are a little bit soluble, we should also note, oops, why is this not writing? There we go. That for aldehydes and ketones, if it's less than 4 carbons, it's soluble. But if it's greater than 4 carbons, it's insoluble, meaning size matters. And then one last little kind of random fact about these types of molecules is that if they have low molecular weight, they usually stink. A lot of the smell that you get from rotting food and various other things that kind of smell are due to low molecular weight aldehydes and ketones. And then if you get to the high molecular weight ones, then they actually smell better. For instance, one of the primary functional groups on cinnamon and spearmint and on most perfumes is at some point or another they have an aldehyde or a ketone functional group on them. Now we'll learn that there are other molecules that are also smelly, particularly when we get to amines and we talk about esters and things like that. But for now, kind of a real quick and dirty test to see if you have a small or a big aldehyde or ketone is simply whether it stinks or not. Okay, so, my ears are popping. That's it for what we're going to cover. I'm going to start in on reactions tomorrow, or Wednesday, I mean. And so what would you guys like to review right now? What would be useful for you? I guess maybe we should point out that homework 23A, and I think you can do most of C, is due Wednesday. I can't remember. Let me look at 23C and see. Maybe there's something I forgot, but... Oh, there might be some things you need reactions for. Let's just say 23A is due on Wednesday. So what else do you guys want to review?